All right, good morning. Let's get started.
Okay, I'll let you know. I'll shoot you an email.
I'm sorry about that Friday. Turns out the TA's cell phone, it updated that the daylight saving time later. So his alarm went off like an hour or so later. So regardless, yeah, I think he came in like 10:40, which I guess most of you are gone by then, right? So I didn't hear anything else about people, so I'm going to let that go. There was one suggestion to not count the exam at all, which I think would inflate the rest of the other grades, right? So I'm just going to call it 100, because even the last one, the average was close to 100. So it didn't seem like it'll affect too many people. I still would like for you to take the exam. It's online, so I'm not going to grade it, but if you want it, I can grade it for you. We'll come back to this topic. We could potentially come back to it in the next modules or all the way to the final exam, right? So are there any other questions about the projects? How are the projects coming along? Does anyone want extension? I was hoping not to give extension because it's Easter Sunday and stuff, but if somebody wants it, let me know. Yeah. What?
Can you just extend it one day?
Sure. I don't even mind extending it past the break, right? But because I think we're kind of like 2 lectures behind on the memory topic anyway, so we'll still be on the stuff, right? Yeah. So. Okay. So in the last class, we left off at looking at paging and the number of different ways you can do paging. Right? You maintain the page table, and the big problem we were struggling with was page table tends to be bigger as the address space becomes bigger. So when you go to a 64-bit architecture, you can't afford to have a really large page table because page table is a per process data structure. So you would like to somehow optimize on the space, but then you have to pay the price in terms of the lookup complexity, right? Especially when you go to 64-bit architecture, you traditionally go to inverted page table, where the page table size is as big as your physical memory, and there's only one page table for the entire system, right? It's not per process anymore; it's per hardware, per machine. But then you pay for it in terms of the search, right? So you need to have a hardware mechanism to do a search efficiently such that it can do this translation for you. And now you push all the complexity to the hardware, and any slowdown on that procedure would mean that you slow down the entire system, right? If you're going to do a linear search on the page table, linear meaning like you start look at the first one and keep looking down, and that means every one of those would be a memory lookup. So if you're trying to resolve one memory address, and if you have to search through 10 addresses on the page table, then you're going to make it that much slower, right? So you're going to pay the price for accessing your data and 10 of these page table entries. You want to avoid that, and it's a big challenge, right? That's where we kind of left off. So that's the notion of, you have a notion of a logical address space, and then you translate that to a physical address space, and that makes it useful. We'll see how it is useful in the next chapter, but for now it's a useful thing because you don't have to have the same address, right? We come back to the notion of segmentation, which is where we kind of started the whole stuff, because applications or your compiler likes to deal with memory in some nice logical chunks, right? So in the little example we looked at, we had a notion of a text or a program. We had a notion of a read-write, some chunk of memory, and read-only memory, and so on and so forth. So from the higher level perspective, it's nicer to call them as one segment, because the users typically request a chunk of memory for certain purposes. So the notion of segmentation is essentially an even higher level concept, right? So you as a program, or the compiler on behalf of you, would make a request for a chunk of memory, And it's not bound by the underlying notion of pages and frames and all those things. It would like to ask it in terms of this logical space. Most likely it will be implemented as a paging concept underneath, because that's the logical way that you would want to do, right? Because paging gives you all these benefits that you don't have to worry about where to find the space, where you don't have to worry about external fragmentation, or you don't have to look for space. Any page is the same. So you build even higher concept, right? So now you have a notion of a segment, which is essentially the one that we looked at from the compiler. The compiler asks for a segment, and then it might be translated into logical pages, which may be translated into physical frames to actually go into the hardware, right? The hardware, the CPU only knows how the physical address, the machine knows how the physical address, but from a program perspective, you call them in segments. And segments may be broken down into a bunch of pages underneath, and that gets translated to a frame to really go on the hardware. Does that make sense? So with the notion of in the segmentation, you have a notion of external fragmentation, because that's what the programs ask, right? Programs ask for something, they don't really care about what happens. They don't really. So when you do traditionally when you do the implementation of segmentation on top of paging, how big do you expect the external fragments to be? In the general case we looked at before, the notion of external fragment is basically the space that couldn't be used by somebody else, right? So if you were to implement segmentation on top of paging, what would your external fragments look like? How big would they be? Can you imagine what's the biggest external fragment you can imagine for if you're implementing segmentation on top of page table? So essentially, if you ask for, let's say, segment which is 2,000 bytes, right? And if your page tables are 1,000 bytes, then you will have to allocate it as 2 segments, right? Two pages, right? So what's the largest external fragment you would see? Yeah?
The size of a page minus byte?
Yes. Yes, the size of the page minus byte, right? So in the worst case, you may ask for a segment, the same example, if you ask for a segment which is 2001 bytes, then you're going to base the other stuff, right? Because from your program perspective, you're only asking for 2001, and it turns out the rest of the 999 would be left out, right? So that's the notion, and you typically use it for all these kind of variables, all the program variables, and we saw the examples of this way when we started the module, right? So from conceptually, you have this notion of having all these segments floating around, right? They may be contiguous, they need not be contiguous. Typically, compilers don't consider them to be contiguous. They only want to make sure that everything within this segment and everything within this segment is contiguous, right? And the way compilers refer to them is usually as start of this and offset from here, right? So they deal with them as they allocate a segment, and then they allocate, and once they know what the segment is, they refer to the constituents as something which is offset from here, right? So let's assume this we don't know what this offset is. So we're going to assume that within the segment, I want the 100th byte, I want the 10th byte, or what have you, right? That's how you programs would want to ask for it, because they don't know where this is going to float. So if you look at them as in the logical address space, they seem like they are floating. So we have no idea whether in the logical address space, main programs come before symbol table or what have you. All we know is within the main program, all the addresses are contiguous. So if I want to access something here, I would say I want it from whatever this is to this offset, right? And if you do that, then you don't have to worry about where the segments get allocated, right? And that's how you would use it from a program perspective, right? Think of this as a matrix, right? When you do a matrix, you say matrix of 10, which is basically saying I want the 10th element of the matrix. So you need to find out where the matrix starts, and then you look for the 10th element. And that's exactly what you're trying to do here, right? So once you have to go through 2 different iterations of how this happens. So you have a logical view of segment, which you kind of translate into a physical notion of a segment where they all are laid out in the logical address space, right? So, and then the next step would be you may implement this as pages. So these all may fit into certain pages. But for now, you assume that all the segments seem like they're floating. You allocate them such that each segment starts at some place. And in the logical address space, they are laid out in some fashion. And then you may translate each of the segments into a page table for actual implementation. But this is how you do this translation. So when you as a programmer ask for a segment, the segment will get allocated as a physical segment, which will get translated to physical pages and so on. Is that confusing? Again, you do this because it's easy for people to deal with it at this level than at the page level, right? The other reason is when you'll notice this, you'll learn more about this if you take a course on compilers, which is when you write a program, right, and you compile the program, you don't necessarily want to know what the page table is. You don't want to know about the page table and all those things, because the page table size is dependent on the frame size. The frame size depends on the hardware, right? So if your compiler is compiling a program for Itanium or a desktop, right? It may have different page table size because that is given by the hardware, right? So the compiler does not want to deal with all the page table issues because that's a lower level, right? So if you want it to be portable, you want to deal with them as a segment, and then you assume that the mapping happens underneath you. So the compiler does not really care about the page table because that changes with the particular hardware, right? It's also more complicated than that. Some of the machines can have different page table size, and one of them is configured when the operating system is built, right? And thanks for pointing out the bug in Arc, which is kind of bizarre. It doesn't really change what your project is, but it's kind of bizarre that I still can't figure out what really happened, right? Because there's some particular number it fails, but it also fails on the EXPSys desktops, right? So those are a different architecture. I mean, one is Itanium, one is a Intel 8086 based machine. It doesn't happen for C programs. If you wrote the same in C program, it works fine. So it's something with Arc, not the hardware, right? So you're free to use either of the fix that folks sent or what have you, right? So that brings us back to the notion of how you use segments, right? So you use segments by figuring out what the segment start is and then the offset within the segment, right? So if you think of this as a matrix, you want to know where the matrix starts, and then you calculate where the element you want to look at, right? And of course, this may get translated into a pages underneath where you are. So if your hardware supports this notion of a segment, which we'll see in a little bit that 83, 86 Intel architectures do, essentially what they're trying to do is the architecture knows this concept of segments, but it also knows this concept of paging, which is what the other things are built on. So you may have architecture support which translates from your segment to pages and pages to frames, right? For that to happen, you need to know where the segment starts and where the offset is, right? So if you load into some place and say, I have one segment, the segment starts at this logical address, and then this is the offset within the segment, right? So you need the notion of segments and how big the segments are. And if you access something beyond that, you would get a fault, right? This is where the segmentation fault comes from. So since you, as a program, deal with it as segments, not pages, you don't call it page fault. Page fault has a different meaning in the next chapter, but for now, this is called segment. So if you access something beyond your segment, you'll get a fault, right? So in terms of segmentation fault, right? Many of you have seen segmentation faults, right? Where do you get the segmentation fault, right? Yeah, so segmentation fault is when you access something which is beyond what you're supposed to access. So if it is beyond the limit register, you should get a segmentation fault, right? So where would you get a segmentation fault? Let's look at this here. So you have a segment, and this is the segment base, and this is the limit, right? Which kind of defines this as a limit, right? And segmentation fault is when you try to access something which is not within your limit, right? So if you try to access something here or here, you can potentially get a segmentation fault, right? So this is sort of easy, right? This is when the limit becomes -1 or something. Where would you get segmentation fault on this side? You get a segmentation fault on the next byte. How far off do you have to go to get segmentation fault?
To the next page boundary.
Yeah, it depends on the hardware, right? Depends on what the hardware will let you do. So depending on where the fault happens, right? If you get a fault by looking at the limit, then the next byte would give you a fault. But if the hardware does not look at that, then you'll get a page fault when you move from segment to a page, right? So this becomes blocked off into pages, right? So if the fault happens at the page level or the segment level, if you check it at the limit register, if the hardware check, I mean, of course it has to be supported by the hardware. If the hardware checks it at the limit register, then you'll get a segmentation fault if you go 1 byte over. But if the hardware did not check it at the limit register, and if it did it at the page boundary, since all the segments get translated to paging at some level, you won't get segmentation fault at this level. It moves up here. Right? It moves on the next page, not the next. So even though you think of it as segments, even though you're accessing something which is beyond your segment, you might not get a fault because there's a translation from segments to page, and if the fault is happening at the page level, that's where you'll get the error, right? So this is one of the reasons why when you took a course on in the programming class, right? Did you understand exactly where you get segmentation fault? Was that made clear to you in terms of where you get segmentation fault? I suspect that you were not told precisely, right? Do you know precisely now where you'll get a segmentation fault? Let's look at this way, right? Let's look at a simple program, and this is text, and this is your read-write memory, right? And all this is in logical address space, right? And your program generates logical address space. Which logical address space would give you a segmentation fault? Definitely, and which one will definitely not give you error? Which one would give you an error? Here you actually might get an error if your page table allowed the concept of, so if the operating system was able to tell the paging hardware that this is text and text should not be modified, if you could say that, and if the hardware can deal with that, then if you try to modify this, you will get a fault, which may be told to you as segmentation fault or some other fault. But you can't guarantee it. It depends on the hardware, right? If the hardware did not know about text or did not know about read-only page, you might not get a fault here, right? What you can definitely say is if you access any of these memory, you will not get segmentation fault, regardless of how you access it, right? Regardless if you're doing the right way or the wrong way, right? So if you have a pointer equals address of I, and pointer gets corrupted, right? You're free to modify any of this variable, because as far as the operating system is concerned, that segment was given to you. As far as the hardware is concerned, that segment is given to you. So you will not get any kind of fault if you kind of chomp around in here. If you go beyond your registers, if you go beyond your arrays and stuff, you can do whatever here, right? You may get a fault here, right? You may get a fault here and here, depending on how the hardware, how the paging and all works out for your particular case, right? So you may run your program twice, and sometimes you may get a segmentation fault, sometimes you don't get a segmentation fault. Most definitely, if you take it from one machine to another machine, sometimes you get more segmentation faults, sometimes you get less segmentation faults, right? There are some architectures which are more forgiving, there are some which are less forgiving, right? Silicon Graphics used to make computers which were less forgiving. If you go past what you're allocated, you get a segmentation fault. DEC Alpha used to be more finicky. Intel tend to be quite nice. They let you do lots of bugs and then it lets you slide, right? So a lot of people, when you program, so back when I was a TA, students didn't like to be programming on the DEC or say SGI machines because they were very finicky. So you could take a particular piece of code, run it on that hardware, it'll give you a segmentation fault, move to Intel-based machine, everything will work fine. And most of the students will be pretty happy because they said that machine is kind of broken because it's giving me more segmentation fault, right? What would you say? You'd rather find the segmentation fault, right? Because there's something wrong, right? So that's the reason you can't precisely tell. If you get a segmentation fault, that means something, right? That means that you are definitely accessing something that you're not supposed to access. So for example, if you access here, you may get a segmentation fault. But just because you don't get a segmentation fault means nothing. It just means that you kind of sliding under the radar of where things are failing. And that's probably why you are not taught where segmentation fault should happen, because it depends on a whole bunch of things which hopefully we are looking at here, right? But as bugs go, segmentation fault is the easiest to fix, right? I hope you kind of realize by now, right? The hardest bug to deal with are the timing errors with the threads and threading issues, right? So we unfortunately found out that the pin tool has some bug, right? So if it runs for many of you send me email about the pin tool, right? After about 70,000, 80,000, a couple of the lines were getting mixed up, right? So output of I think 2 threads were getting mixed up. So you're getting rather than, so one of the errors you're getting was going on like this. So it's probably getting the X from one thread, the 0x from another thread. So you're kind of mixing it up, right? So those kind of bugs would be really, really hard to fix, the pin tool stuff, especially because it's happening when you are multi-threaded. Segmentation fault is easy to fix because you kind of know, you get some kind of indication, right? So that's not a segment, right? So I don't want you to be confused. So we talked about contiguous allocation and segments at the beginning of the semester. Then we said paging is the easy way to deal with it because paging makes all the allocation units the same size. So allocation becomes easy. You don't have to worry about anything else. Then we come back and say, well, paging is easy, paging is nice, but the programs don't want to deal with it. So we're going to create an abstraction of a variable size chunk called segments on top of paging, right? But this is sort of pseudo because it essentially translates from the segments back to pages, which gets translated back to frames. So we get the best of both worlds by increasing the complexity of the hardware, but now we get come kind of full circle, right? So we're going to talk as if these are segments, but essentially they are underneath being translated to pages and frames. So when you talk about segments, relocation, from your program perspective, you expect to be relocated as a segment, right? So when you talk about pages, you expect, one of the things you can do is I can take the page which used to be in one frame, put it on another frame, and if I do the page table right, then essentially you can continue to access it in the same logical address. Now it has moved, right? But if you're dealing with it as segments, you have to do it for all the pages, right? So in a sense, you can't just translate it. You have to assume that if you were to relocate one of them, you have to make sure that all of them are still all of them are still accessible, right? When you share them, you can share them as segments. So that's one of the ways that you will implement sharing. So if you want 2 programs or 2 threads, 2 programs to share your some chunk of memory, you would refer to them as segments in your program, and you'll have to translate that into pages in the hardware. And you can think of the allocation as best fit, worst fit, external fragmentation, but essentially that's a logical view. So you move from one logical view to another logical view, and then go to the hardware view, right? And you again think of the validation bits to be for the whole segment, right? So from a program perspective, we call them as a whole segment. So if you remember, we call the string variable as read only in the assembly language code, right? A compiler called it read only. So you want the whole segment to be read only, even though that may translate into multiple pages, each of which will have to have the same stuff as what the segment did. But when you think about it, talk about it in a segment fashion, you think of them as one logical unit, right? So it's important to not get confused by the fact that this is not the same as the one we talked about before. This is a logical view of what the paging appears to you. So the way you would implement this is, if you have it's sort of like your page table now, right? You take the address, you figure out what the segment is, and you take the displacement. Displacement you'll have to compare now with the limit register, right? So you have to take the segment, go to a segment page table, segment table, right? Segment table will have the notion of the limit and the base, right? So you take the base to go somewhere. Limit you can check if the hardware checks it. And if the limit is within, if your displacement is within the limit register, then you can let it go, or you can get a segmentation fault, right? You don't have to do this stuff. If it doesn't do it, then you'll get checked over here, right? So this way, you're adding another set of tables, another set of stuff. So your program will call it as segment and displacement. And what do you get here? What is this address you get here? Is it a logical address or a physical address? It depends on what the hardware wants, right? It is possible for you to implement segmentation in hardware itself directly, though very few machines will do that, but you could do that, right? But more likely this is a logical address, so you'll have to do another translation from logical to physical, right? Because of the benefits we said. We don't want to do the allocation on variable size stuff. So most likely this is a logical address which you get translated again to physical address. But you add one level of complexity, right? So if you had, if you take that program, right, some logical view, if you have the segment table, which basically says that segment 0, limit is 1000 and base is 1400. So from 1400 to 2400 is segment 0, right? So in the logical view, that segment with the segment table becomes this in logical address space. And of course, you're free to translate this from here to physical address space using paging or what have you, right? So this is the logical view of logical segment address space becomes logical address space, linear address space. Let me proceed from there. And if you want to share, so essentially you can set the shared address, right? Like this segment is shared between these two processes. So that gets put on each of the segment table. So each of the process will now have a segment table which maps to the same segments, right? And Multics, which is the operating system which came before Unix, implemented segments using paging, and most of the subsequent machines do the same thing, right? Back in 70s and stuff, there used to be lots of exotic machines. Each one of them was they were innovating a lot, so you could have hardware which supported segmentation all the way through kind of stuff, which is less and less true now. I mean, the number of hardware is standardizing to a few set of architectures. So in the Multics time, when they did this, it was considered fairly innovative. Before then, they used to have segment view all the way to the hardware. And by doing this segments from your operating system to the page table at the hardware, you sort of get the best of both worlds, right? Paging, like we argued, is easy to manage, easy to deal with, easy to allocate, and all those things. So now you get the flexibility of calling it into segments and the flexibility of doing paging. So Multics introduced it, and now most of the operating systems you see follow this model, right? So in terms of the way the Multics assume what happens is, it figures out based on the segment table the segment address you have, the page table which corresponds to that segment, right? So for each of the segments, you have a page table, right? So each of the limit, it checks to see if the limit is within what you're supposed to do within the segment table. And then essentially that's the logical address, right? So you take the base table page to figure out what is the page within that segment. Does that make sense? So the idea here is you have a segment, right? This is the base and then the limit, right? So this page, if you do it with paging, let's say this is P0, P1, P2, right? So one way to implement this would be to say you have one large page table, right? And basically do a translation from segments to the page table in the large page table size, right? But what optimization you can do is you can have multiple page tables, have a small page table here which only has 3 entries, right? And this points to frame 0, frame 1, and frame 2, right? Since you have only 3 pages here, I use this page to figure out what this page table is. So the first page here would be the first page within this table. Second page here would be the second page table here. So this way, the page table size is only as big as the amount of logical address you use. Does that make sense? You could implement this as the whole page table, right? And then point from here to the corresponding entry. But it's wasteful because you know that anything here is not being used, right? Because anything behind here is not being used. So you could avoid this extra wasted space by having a page table per segment where the entries are basically only for the segment size, right? So depending on how many segments you have as many page tables. Each page table only translates from here. So first you have to make sure that you find the right entry and you get what you want. You cannot access the logical address space. So you cannot access logical address space something here because you couldn't have come here through any of the segment tables. Does that make sense? Actually, this is what the 8386 does. So you're gonna have one segmentation table, and you're gonna have lots of page tables. Each page table per segment, and each page table size is determined by the size of the segment, right? Can you make the segments so if you have this architecture, how do you make the segments bigger? After you started the program, can you make the segment bigger? Can you allocate more space on your segment? I think this was asked in the homework assignment, right? Like variant of this, right? How do you make this? So this was the segment which you used to have, and I want to make it go this far. Can I do it? And if so, what do I have to do? So I had page 0, page 1, page 2. Now what I wanted would mean that I need another page, right? So what are the things I have to do to make this happen? Let's start with the limit region. What happens to the limit value on the segment table? Right, the segment table basically has the limit and the base, right? If you want to make the segment bigger, what do you change in the segment table? You would have to increase this, right? You have to increase this to reflect the new size, right? And since it's a new page, that page will have to be allocated from the frames, right? But that's not enough, right? Because if you allocate a frame, you will have to add it to the page table, right? Since there's a page table per segment, you have to make this page table bigger, right? You can't just increase the limit size, because limit size would mean that now you have to have mapping for one more page, which means that this page table has to be increased, which means that you need to make this allocation bigger, right? So how would you allocate this page table? This again depends on the hardware. Is there any size restrictions on this page table? Or is it also bound by the page table size? Did that question make sense? So if I wanted to go beyond this, I said I need to allocate one more page. Can I make this page table size grow in arbitrary size, or does it also have to grow in page table size? Makes sense, right? Can you make it arbitrary size? The answer is you can't. Even though we call all this page table and all those things, from a hardware perspective, it's going to treat everything into one size, right? It all maps to the frame size, right? Frame size is the unit that the machine knows. All this mapping is just for us, our convenience, right? Remember, the page table is some concept that if you tell the hardware, this is where you should look for a page table, that's what gets allocated. But it's not fixed, right? So if you have, let's say you're a frame, right? Basically, to the hardware, what you say is, you're going to define this as frames, because the hardware knows what it is, right? You're going to say, this frame, treat this as a page table, right? This frame, treat this as a segment table. This frame, treat this as a data, whatever, right? But the hardware knows everything in frames, right? So if you want a page table here, so let's say this was allocated to text, and this was allocated to data, and this was allocated to paging use, right? You're still bound by the frame size. So if you want to make this larger, you have to make sure that there is enough space here. If not, you'll have to allocate another frame and make it that much larger, right? So there's a notion of a frame, which is fundamentally what the whole system knows, right? It's fixed size. There's a notion of a page, which equals the frame size, right? And this is logical and this is physical, right? And then based on that, we are going to build a data structure called page table, which is basically an array of large array, which gets allocated using pages, which will eventually be converted to frames. Then now we are talking about adding a segment table, which is allocated as pages, which gets mapped to frames. So every allocation you do on the system is all bound by the frame size, right? You do this translation back and forth, but they all have to be on the frame size. You can't allocate pages larger than frame size, which is different from page size. You can't allocate segments different than page size, the way you split it. Your page table is also bound by page table size, which means that if you want to make the segment larger, right, in logical address space, you may be able to find some space here, but here you have to do the same thing for the page table. So if the page table was such that something else was logically here, then you can't make the page table grow bigger, which means that you can't make the segment grow bigger. Right? You need to be able to grow in the logical space, so you need to have this little spaces. Right? Is that? I think the way it was asked in the homework assignment was we were looking at it like this, right? Let's say text, data, and hash, whatever, right? This means this is all the way it's laid out in the logical address space, right? If you wanted to make this data bigger, you can't really do it because this logical address is being used by somebody else, by the hash, right? So you are better off like this, because then you can grow these things, right? If the data segment begins to grow, it can keep growing till it hits the next logical address space. And the same for the page table. So if you allocated the page table here, the page table can only grow that much before the logical address gets allocated to somebody else, right? I seem to have lost many of you, but hopefully, if you think about it, right, the frame size is the atomic unit, and you are forced to keep the frame size, and everything else kind of follows from that, right? You cannot make allocations smaller than that or bigger than the frame size. That means your pages have to be the same size as the frame size. Your page table has to be multiples of page size, which is the multiples of frame size, which is same as frame size. And segment table, everything, right? So this is sort of what your 8386 hardware does, right? 8386 supports segmentation and paging. So it knows about the concept of segmentation, it knows about the concept of paging, even though segment is a logical notion, right? And paging is translation from logical to physical. So when you call a logical address, right, it knows that it's part of a segment and a offset. So it will first look up on the segment table to figure out if it's which page table you have to look at. And the page table is actually a two-level page table, right? It's a hierarchy. So first you look at the first level page entry, which is called directory, and then you look at the next page level, right? So each page for a segment is two-level. So you have to figure out which directory you're going to look at, and within which directory, what's the upper level, what's the lower level. It's a hierarchy of page table, right? So basically, if you do that translation, you get a logical address here, and then you do the logical address to physical address translation using a two-level hierarchy, right? So for every address you're issuing, your hardware is doing this translation from segment to logical address to physical address through two levels of hierarchy to get what you really wanted, right? And so you can imagine the complexity, right? So when you build the operating system, you have to be aware of this stuff. You have to allocate all this stuff to be given at the right spot. And in terms of performance, right, all these lookups, they don't look as expensive to you, but the segment descriptor table is in memory, right? Which means that it's stored in a page on a frame. So you need to translate. You need to make sure that it's either in cache or you have to pay the penalty, right? And all this are in memory, right? So unless you can keep them in cache, you're going to pay the penalty, because otherwise, to do this, I need to look up that table. I need to pay one price. Look up this table, another price. Look up this table, another price. So to access one memory location, I have to pay the price for 1, 2, 3 extra stuff, right? So what is what would you call the cache for this, for doing this?
TLB.
Yeah. That all of you have to know, right? So essentially that's the TLB stuff, right? And again, this is done by the hardware. We as operating system have no control over it, right? How do we, so like I keep saying this is up to the hardware, right? Is there anything you think we can do to influence the hardware designers? How do we influence this stuff, right? Do you think this is a good architecture? Knowing what you know about memory management, does this sound like a good way of allocating memory from the operating system perspective? If you want something to be changed, how do you change it? How would you change it? There's no magic. You talk to Intel, right? Or you talk to Motorola, right? And trust me, they won't talk to you because they don't want to do all this stuff, right? If they're talking about a fast processor, all this mumbo jumbo is not what they want to do, right? All these things slow the program down, right? They would much rather have not to worry about anything. If you say, I can deal with physical address, no logical address, they'll be happy to give it to you because your process can be really fast. Some of you are taking a hardware class, right? You'll notice that the TLB is not exactly walk in the park. I mean, TLB is a very complicated thing to build, right? How many of you looked at TLB in the hardware class? That's pretty few of you, but I thought more of you are taking hardware, right? TLB is not a trivial thing to do. TLB takes lots of space. TLB takes lots of power and everything. But they're forced to do it because operating system folks say, we can't deal with physical address, right? So this comes up after compromise with the OS person and the hardware person, right? So Intel wants to get rid of the whole thing, so you have to come up with the kind of stuff, right? So Intel is willing to work with you. They want to work with you because they want to make this as fast as possible. Because if you don't, you'll find that these 3 lookups would mean that your system will go, let's say, 1/4 of the speed of what you thought it would because it's doing all this lookup, right? So if there was a competition, if say AMD can come up with a different hardware here, where you can only need 1 lookup, so what will happen is AMD machine will look as twice as fast as Intel, even though they're running at the same speed, right? Because the speed that you see from a machine includes all this cost, right? So if each memory lookup takes 4 time units here, because it has to do lookup there, 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 whereas on the AMD side they can do it with 2, where all this is like 1 lookup, let's say, then AMD is going to look good, they're going to win, right? So hardware and operating system are basically kind of glued together, right? They're not separate. So if you look at the hardware side, they have to do some things to make sure that the software people are happy, and software people need stuff from the hardware. You can't do stuff without each other, and that's the reality of it, right? And I'm going to stop with the last slide. So essentially, Linux uses 6 different segments, right? And the reason it uses 6 different segments is Linux wants to be portable across different hardware. So you can't really trust that newer hardware will have a lot more segments. So they try to reduce the number of segments, right? But if you were to write a machine which is very tuned to a particular hardware architecture, you could think of a different segment for everything you want, right? So every variable can be put in a different segment, right? Is that something you would think about doing? What would be the benefit of having lots of segments? 1 segment per variable. Each of the variables you ask for goes in its own segment. Is there a reason why you would like that? The answer is related to a segmentation fault, right? If it's fine-grained like that, then anytime you go beyond that, if you go past the array index, you'll get a fault, right? So from a program perspective, you want as many segments as possible because then you get more finer detail of if you violate something, you get a fault right away. But if you do that, then it won't be portable because now you're dependent on the hardware. So on some machines it may work, on some other machines it may not work, right? So The compromise, what they do is, they know that if you're buying a server, you tend to buy certain MMUs. So Intel can say, if the MMU is blah, do certain way. If the MMU is something else, do certain way kind of stuff, right? So that's why you have variants of operating system, one for desktop, one for server, and all those things. They can play all these games, right? I'm going to stop here. We'll continue with the virtual memory on the next lecture. So far, I only heard extension up to Thursday, right? If anybody wants later, let me know for the program.